Hi everybody, welcome to Activity 2, Lesson 2.1. Today we are going to be starting on page 13 in your Springboard books, and you are going to need a pencil, a highlighter, keep that vocabulary list handy, and a calculator if you need to reference anything. Now, the big vocab word of the day that you are going to see on here is inductive reasoning. And what inductive reasoning is it's the process of observing data, recognizing patterns, and making a generalization that we call a conjecture. So basically, we do inductive reasoning all day, every day. So take a moment to read through this first example and talk about what you think the reason is all of these people got sick. Now, hopefully you noticed on here that it was because of the pasta salad that they got sick. So even in today's world with COVID-19 and we have these contact tracers, it's a lot of what they're doing is figuring out where did these people get sick, very similar to this food poisoning scenario. Now, the next part of the notes, what I want you to do is to go through and test out these patterns here. So very mathematical patterns you're going to see, but you're going to come up with what are going to be the next two terms in each of these sequences, and what is the pattern, what's going on each time. So come up with those next two terms for each of these. Now, hopefully you notice down here in part D, I know this one's usually the trickiest that some people get wrong, and a lot of times it's kind of hard to see at first, but notice that if you take the two previous terms, in this case 1 and 1, if you add them together, you get 2. And then 1 plus 2 gave us 3. And 2 plus 3 gave us 5, the next term after that. So then we have 3 plus 5 giving us 8, 5 plus 8 giving us 13. So we're just adding up the two preceding terms, and that's how we're getting 21 and 34. Now, this is a very special sequence. If you notice this math history box over here, it is called the Fibonacci sequence, and Fibonacci is a really famous mathematician back in the day. And so he's got his own special sequence. They came up with this that are used in a lot of different mathematical things. Now, moving on to the next page, notice here, we're kind of skipping down a little bit. And what you are going to notice here is that we are going to look for a pattern based on these overlapping regions. So what we're going to have to do is we're going to have to start by drawing in some lines. So we're going to kind of connect the lines and then count the number of regions. So if we have 2 points on our circle and we connect them, we are creating 2 different regions. We have region 1 and region 2. So we have, if you go up here, 2 regions. Over here, though, if we start connecting, let me do my line tool here. If we start connecting our lines, what we're going to notice is we have connections here to here, 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 here to here. And what we've created this time is 1, 2, 3, 4 regions. And if we have 4 dots on our circle, 4 points, what we're going to notice is as we connect these, we have, again, 1, 2, 3. Then we're going to connect from this one to the one that's not touching these. We're going to have a total of 1, 2, 3, 4, 5, 6, 7, 8. Now you might start seeing a pattern by now if you want to take a moment to predict what do you think region 5 is going to be. Well, to officially test that hypothesis that you just wrote down, we have 1, 2, 3, 4 diagonals. Keep connecting here to all the points on the circle that it's not already touching. And what we're going to notice this time is we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 regions. So as we look at this right now, what we could kind of deduce here is that each time a point is added here, so each time we add a point, what we're doing is doubling the number of regions. Okay, now keep that prediction in your brains, and we are going to move on then. We're going to need that information a little bit later. All right, now taking a moment here to look at number 5. All right, they're asking us, does it seem illogical that Mario conjectured each time we are taking this and rotating it 90 degrees? Well, we can kind of test this particular one out by taking a little screenshot of our picture here. So we have our triangle. And I'm gonna shrink it down a little bit. So we have our picture here, right? And if we rotate it 90 degrees to the right, here, clockwise, to the right, we notice we get that. And if we rotate it again, we get that. So what we could say is that Mario's conjecture is in fact, it makes sense, it's reasonable, because when we tested it out, it does look like it indeed rotates 90 degrees each time. Right, try number 6 on your own for a second. What do you think the conjecture would be? Hopefully you're noticing that each time it seems like she is doubling her distance. And for part B, there a way you could check that, just go out and watch her. Check her records. See if we check out her Apple Watch or her Fitbit, did she actually run 4 miles that week, to see if the pattern is continuing. Okay. Now, after that little break, we're going back to what we had over here, right, on this last one. Now, we said that our conjecture was that each time we added a point that the regions were going to double. So if we added another point here, let's say we added a 6th point, how many regions do we think there would be? Well, we're probably thinking double 16 is 32. Is that in fact going to be the case? Well, if you guys flip to the next page, page 16, you're going to see your regions here. Now, when you connect the dots, what you are going to notice is even though we have 6 dots, there only ends up being 31 regions, okay? Now, looking at that, what this basically does is it kind of screws up what our conjecture was, right? There's actually only 31 regions here, and it didn't fit our predicted pattern before, right? There's definitely going to be some kind of change now each time as we added those points. It doesn't fit that conjecture. What this ultimately tells us is that we can't always base our facts on conjectures, right? Conjectures don't necessarily hold true unless we prove them. So inductive reasoning sometimes will have some flaws, okay? So that's where number 8 comes into play when it talks about if a conjecture is true for the first few terms, is it necessarily true for all of the terms? The answer is no, not necessarily. Without proving it, we don't necessarily know in the long run if that's going to hold true. All right. Let's see. Last one we're going to do together, and then we'll finish number 10 on your own. Number 9 says here that the table below represents this function here. Based on this table, Trent conjectures that the values for f of x are always going to be positive. Is that necessarily true? Well, the answer again is no, because as this pattern continues, as numbers are getting larger for x, sure. But the problem is if we start testing out anything that is less than -2 on this chart, well, if we test out -3, for instance, and we plug -3 in for x, we would have 2 times -3 plus 5 which is in fact -1. So what we did here is we disproved his conjecture because we were able to come up with something that made the statement, his conjecture, not true. All right. Have you guys finish up with number 10 on your own? All right, thanks for watching. And next lesson, we will talk a little bit more about more reasonings, including deductive reasoning.